When you're designing a mobile robotics, either for competitive robotics like FTC, FRC, or VEX, or for hobby robotics in your own personal project, the most important thing for a mobile robot is the drivetrain. You just have 4 simple traction wheels, having a center rotation in the middle to be able to go up and over. It allows them to move around pretty freely, better, but one point in time you always have, it does have holonomic. These are really commonly seen. I'm Brogan Pratt and I've been tutoring robotics and design for over a decade now. I'm going to show you the most popular designs for making in 2 orientations, a tank drive orientation and holonomic orientations. And for each individual setup for those drivetrains, I'm going to tell you why you might want to consider using one of these, what its pros are, and what some of the drawbacks are for using this design. Let's talk about what exactly a tank drive setup is, because there's many different ways that you can set up a tank drive chassis, but they all kind of follow the same principles. And for the most part, a tank drive has a pod on the left and a pod on the right, and each pod or each side of wheels is independently constructed. Tank drive is probably the easiest drive that you can set up to create for a robot chassis. It's got really strong pushing power and it's pretty easy to control. You can either control it with a single joystick, just like how you control things when you're driving on a video game using arcade drive, or you can have 2 joysticks where one controls the left side of the robot and one controls the right side of the robot. Some of the big drawbacks of tank drive is that they aren't very fast. They can have some wheel drag or wheel scrubbing when you're trying to rotate, and they're not the fastest at navigation. However, if your project needs simple design, you're maybe new to competitive robotics, something along those lines, or maybe you just don't need a very complex idea, a tank drive is a great place to start. If you're thinking about a tank drive setup, there's some questions you can really consider. Does your task involve pushing objects or resisting some sort of external forces? A tank drive is a great time to use one of these. Is your operating area pretty open and clear, or is it filled with a lot of different obstacles, meaning you're going to have some pretty intricate movement? And is simplicity in your design and programming as simplicity a really high priority in your project? If so, you should probably use a tank drive in your setup. It's really good for direct pushing power or maneuverability. It's great for anybody who's new to starting out robotics. You can start things really simple, get things out right away. If you're on the competitive robotics side of things, this is great for defense-heavy games where you need to be able to hold some sort of position or some sort of pushing mat. If you have some sort of holonomic drive, if you're aware of what those are, drives that can move in any direction, it's really easy for you to get pushed around. So, there are 4 common types of tank drive. The first one is a pushbot. This key characteristic of pushbot is you've got 2 powered wheels, and you have 2 sort of free-spinning omni wheels. So you have 2 powered wheels at the back and 2 kind of free-spinning wheels at the front. Let's take a look at some examples of these. This is a really simple robot that's driving around. We'll go back and watch that one more time. You just have 2 powered wheels up at the front here and 2 wheels that are omnidirectionally capable of spinning and moving in another direction. You've also got this robot here where it's got 2 free spinning omni wheels and 2 moving wheels in the back. This is sort of a Tetris starting robot. You can see that it's not very strong at being able to move yourself around, but a key benefit of this is it's really easy to get it up and started. So it's extremely simple to get started, yeah? You need 2 motors, you need 4 wheels, that's it. It's low cost and it's low weight. It's pretty cheap to get things started and it's a great place to start learning. When you're really learning robotics, you want to keep things really, really simple. Now, it's got a lot of minus points. There's not a lot of traction. It's not very easy for you to turn around. Your center rotation's at the back of the robot instead of in the middle of the robot. So a lot of things could be improved. So when might you want to use one of these sort of pushbot or simple 2 motor with omni wheels in the front setup? Is it a simple educational task? Is it non-demanding? Is your drive surface smooth? Are you trying to keep costs really low as much as you can? Great time to use a pushbot. When should you use a pushbot? Basic educational, realistically. In competitive robotics, you're almost rarely going to see these at a high stage. You'll definitely see them at the start in lower level competitions, but it's really challenging because you don't have a lot of pushing power and you don't have a lot of maneuverability. So trying to keep a simple robot like this is not going to be very competitive if you're an FTC, FRC, VEX, any of those competitive robotics sort of things. The next style of a tank drive is a 4-wheel drive. And this is characteristic where all 4 of these wheels are powered. It can either be linked by a chain, or it can be having 4 individual motors, as you have seen in this example here from Go Build Us Hammerhead chassis. Now, all 4 wheels are traction wheel setup, and this typically means that these wheels are not omnidirectional. Like in this back one here, you have something called an omni wheel, and they have these little rulers on the side that allow them to move left and right and rotate along these axes. It's omnidirectional, whereas a traction drive will typically only spin forward. Let's take a look at a FRC team driving around one of these. You just have 4 simple traction wheels. You can see there's a little bit of wheel scrub in that it doesn't actually turn rotate very quick. But this one has a light robot, and it's not bad for going forward and backwards, but turning is not fantastic. So, what are some good things about a 4-wheel drive with 4 traction wheels? Well, one, it's really simple to drive again. It's not very challenging. You can even have both these sides linked to the same motor. So programming is not any more complex than a Pushbot. It is pretty stable. For straight line traction, you've got really strong because you have 4 traction wheels, and it's pretty common. It's buying forward, put on. Some minus points on it. It's not great at turning. Unlike your Pushbot, you're actually going to get better turning with a Pushbot than you will with a 4-wheel drive robot that has 4 traction wheels, because your center rotation may be in the middle, but you have a little bit of wheel scrub. Typically, you should have enough power from your 4 motors to be able to overcome those. These things can rock. If you're on a sort of non-flat surface, you're driving over rocks, you're driving over forest, whatever, one wheel can lift off, and then you have a center of mass that's no longer balanced in the middle of your robot. Sometimes these chassis can get stuck. They can get high centered in the middle of an object, and then you may not be able to have all 4 wheels done. Some consideration questions to think if you're considering a 4-wheel drive. How flat and smooth is that surface? Do you need precise and smooth turning? Sometimes you can kind of jitter as you turn around a corner. If you use these high grip wheels, are you okay with a little bit of wheel skid depending on what surface you're using? When should you use a 4-wheel? If it's a great starting point for people just getting into robotics, and it's a miles better than a simple Pushbot that just has 2 motors. In competitive robots, you see these a lot in VEX, but in FTC, FRC, we typically use omni wheels on top of this, like omni wheels on one side, so you can still have all 4 wheels powered, but you can still get those benefits of better turning. Or we move into something like a 6-wheel chassis, which has some sort of drop center, which is our next thing we're going to be talking about, which is a 6 to 8-wheel drives with a drop center. If you're going to be using a tank style, this is my preferred method for most robots, unless you're on the educational starting simple. Once you start getting a little bit more advanced, these start to become quite viable setups for rovers. Some key characteristics of these: they have 4 to 6 powered wheels. Their middle wheels may be dropped, and they may include 2 to 4 omni wheels. So in this setup for one of my past tutorials, I have 2 omni wheels in the front and then 4 traction wheels at the back. And let's take a look at some of this drop center, sometimes called drop center drive, sometimes it's called West Coast drive. So we can see a robot driving around here. You can see it's actually pretty quick at being able to turn around. The wheel scrub is not too bad because at this point, you only have 4 wheels contact the ground instead of all 6. There's another point here from a West Coast drive. You can see that this robot sort of tips a little bit. That's because the bottom wheel is dropped slightly lower than the rest of the wheel. And because it is, you're only having to turn on 4 wheels instead of turning on 6. So you still get some benefits of having a 6-wheel drive and the extra stability that has, and having a center rotation in the middle of your robot, while you remove some of those detriments of having all 4 wheels kicking on the ground. And the last example here, we have 4 omni wheels on each corner and then 2 traction wheels in the middle, and all 6 are powered by a gear train. So why might you want to use a drop center robot? Again, that drop center is this middle wheel, lowers it down, so you only ever have 4 wheels contacting on the ground. It's got much better turning than your standard 4-wheel because you can have 2 different centers of rotation. You can also have, you don't have as much traction as you're spinning around, but you still get great traction for being able to push things forward. So it does compromise a little bit of traction, but it still allows you to have better maneuverability than a straight 4-wheel chassis does. And it gives you a much wider wheelbase, which is pretty huge. Now, one of your minuses here is that you do have that rocking motion. So your robot ends up being a little bit unstable in acceleration, especially if it's on a tall arm. It can have a little bit of wiggle. So that's something to think about. You need to be able to precisely put that middle chassis in the middle. So if you're not using strong enough components, you may not be able to set up that drop center accurately. And then while it's still able to be moved around, just like all tank drives, it can still be pinned because it's able to be rotated around, or you end up getting stuck on points you have to back up. Some other common configurations, you can have as we saw in that previous video, 4 omni wheels in the corners and 2 tank drive. This one, of course, sacrifices a bit more traction, but you're going to get much better rotation points with their center rotations in the center of your robot. You can also even do an 8-wheel. On an 8-wheel, typically the middle 2 wheels are dropped and they come a little bit closer. Some consideration questions if you want to do a 6-wheel drive or an 8-wheel drive with a drop center. 1, does your task need a balance of strong pushing and agile turning? I'm a big fan of this. Is there a tall attachment robot that might be affected if you have some sort of rocking motion? You might want to do a 6-wheel or 4-wheel drive if you don't want to have that rocking. Are you personally capable of manufacturing that frame to be able to drop the center? Do you have those abilities? So if I had to pick a tank drive, this is my favorite way of picking a tank drive. It would be a 6-wheel with a drop center. Especially in competitive robotics, this is quite common in FRC, and it's a great balance of performance and relative ease of assembly. Especially if you're on the newer side of things in FRC or FTC, this is a quite simple drivetrain to build, get up programmed. It's also not too complex to drive around, and it can be competitive at high levels, especially if you have a game that requires a lot of defense. The last style of tank drive, of course, is where tank drive comes from, which is literal tank treads. You have 2 motor pods, sometimes 2, sometimes 4 motors, and then you have interlocking treads or a single band that actually runs around on these. So let's take a look at some of these. This is from an FT example. Tank drives are great at climbing because they're capable of moving themselves around. Now, this is a little high center to the back. And then, of course, we have James Burton's video here of a little 3D printed tank drive, and it's quite good at driving over lots of different terrains. And that's one of the main benefits of literal tank treads, to be able to go up and over a whole bunch of different types of terrain. You can also cross gaps pretty easy on a tank tread. On wheels, if one of your wheels comes off, you don't have power across your entire track, but on a tank tread, you do have that. So if you need to cross some sort of gaps. You also have great traction with tank treads because rather than just having 1 wheel, 2 wheels, or 3 wheels on each individual respective pod connecting on each side, you have the entire section is grounded to the floor, or to whatever surface you're on. So lots of great traction. However, what you gain in traction, you lose in speed overall. They tend to be pretty inefficient. They're very power hungry compared to wheels. Just like with your 4-wheel or 6-wheel chassis, you have a hard time turning. In fact, it's almost sometimes worse because now you scrub across an entire flat length. Treads also tend to be pretty high in maintenance. They have parts that can break. It's difficult to keep things properly tensioned. So it's a lot to keep in mind there. Some more considerations. Do you need to go across really uneven terrain or cross gaps? Tanks excel in that. Do you need that climbing ability more than speed and agility? And are you prepared to help manage some of the mechanical complexity that comes with doing tank treads to be able to do that repair work for it? You should choose these if you're doing some sort of outdoor, all-terrain vehicles. Bomb disposal robots are great at this. Or any application where you have really uneven ground. Yeah, and you need to make sure you have stability across all these different terrains. In competitive robotics, maybe if there's really high terrain issues, or you need to do some sort of climbing. Otherwise, in competitive robotics, you typically don't see tank treads just because they are so slow. Their maintenance is really high, and they do not turn very well. And typically, competitive robotics either favor high defense to be able to push things around, but a balance of being able to move around quickly. Because even if you have high defense stopping other robots from scoring, you still have to be able to move your robot around agile. What exactly is a holonomic drive? Holonomic drives are essentially a robot chassis that can move in any direction freely, forward, backwards, reverse, sideways, or diagonals. Their best ability with holonomic drive is their agility and their ability to move in any direction. Problem with these is that because those special wheels do give them agility, it's also a main drawback on their design itself, and that their traction tends to be pretty poor, and they are pretty vulnerable to being moved around, or they can't make it up steep surfaces, things like that. Some of the most common types we'll go through today are Mecanum drive, X drive, Kiwi drive, H drive, Swerve drives. So holonomic drives are not the end-all be-all and the best robotic train that exists. Some questions you need to ask yourself is, is the primary goal of your robot to be fast and agile, or is it to be pushing things around? Does your robot need to make really small, fine, precise adjustments, or can the parts that are on top of the robot do those fine adjustments instead of the entire chassis itself? And holonomic drives tend to work best on smooth, flat surfaces. So if you're not using one of those, holonomic drive might not be your right choice for you. So they're perfect when you need a robot that can move things around. They're also a great choice in many competitive robotics games that don't need a lot of direct pushing or heavy defense. So let's take a look at Mecanum drives first. They're typically 4 powered wheels, so you need at least 4 motors to be able to do those. And there's anywhere from 4 to 8 different 45-degree rollers, which is called Mecanum drive. So we can take a look at some of these robots driving around. So we've got a robot that's capable of moving upwards, sideways, diagonally, in any of these cases. There's also another Mecanum drive test here that allows them to move around pretty freely in any direction and any axis, which is one of the huge benefits of Mecanum drive. So they can move in any direction they want, and they typically have pretty simple square frames. And then their lateral movement's also quite intuitive when it comes to actually driving it. You've seen these in forklifts around before, and that they're actually pretty intuitive to driving things around. Some of their main drawbacks is that they don't have a lot of friction, and to be able to push them around, because there's the angle rollers that does allow them to move around, it does make it more challenging for them to be able to be pushed. They need flat surface to be able to work, and depending on the design, especially compared to just a traditional flat wheel, these wheels are expensive and they're a lot more fragile. Some things to ask yourself is, does your robot need to be precisely aligned as it's moving around? Are there any sort of side impacts that the robot might face that might damage some of these wheels? Is the floor going to be flat? And that's going to be a question for just about all of these. So these are great when you have a bit more budget to be able to work on. But if you don't quite have the budget to be able to get a Mecanum drive, there are other drives that do exist. A popular one of this is Kiwi drive. So Kiwi drive has 3 omni-directional wheels that you need less motors to drive this, so it's not as power hungry. So we can take a look at Kiwi drive here, where depending on, at one point in time, you always have 2 motors that are being powered. So you don't need 4 motors to drive around. Sometimes you'll have 3, like it is with this robot currently spinning itself around. Now, one of the best options for a Kiwi drive, like we see in this BattleBot Omnis, is that you only need 3 motors. So for really power-hungry systems, it's pretty good. It's also pretty light and compact in that you can make Kiwi drives quite small because you only need 3 wheels. They're a little bit more complex to program than a Mecanum drive, but not crazy. They do have lower pushing power because they only have 3 wheels. And they can be unstable sometimes because of the 3-point base. So if one of those wheels come off, rather than having 4 or 3 more contact points, they can run a traditional 4-wheel chassis, you end up losing some of those contact points. So another thing that's also kind of awkward about this is that because it defines a triangle style drive, it makes it a little bit awkward to move it around and to build things on top of that as opposed to building on top of a square. So the best question you ask yourself is, do I need a really small robot that is not very power hungry? If that's the case, Kiwi drive's probably good for you if you don't need a lot of pushing power. So these are best for really kind of specialized small scale robots or really low budget builds that still wants a holonomic drive. For competitive robotics, unless you're building a really small robot, we typically don't see a lot of Kiwi drives around. Maybe in small scale programs like Vex IQ, you might see some Kiwi drives around, but it's not super common. Another side of sort of budget constraint on a Mecanum drive is something called an X drive here. So it does have 4 powered wheels, and they're set up in an X-based formation. So you can kind of think of this getting a little closer to Mecanum drive. If you had the budget for it, Mecanum drive is still better, but an X drive is not a poor example to come in here because it's sort of a step up from Kiwi as well. I'd say that provided you can have a square base, this is a pretty big improvement over Kiwi drive in most settings. It's going to be faster on 45-degree angles because of that. It offers a little bit better holonomic movement than a Kiwi drive does, but similarly, not very strong against pushing. It's probably even worse against pushing than a Mecanum drive is. Sometimes your frame shape, it's an improvement over Kiwi drive and your Kiwi drive for the triangle. But because it is this kind of, you have these angular wheels, you can still put a box frame on or on top, but it still does having some of those problems of that mounting. Some other questions here to ask is, again, you're kind of budget constrained. Do you have a little more budget than Kiwi Drive, but a little less budget than you would be able to buy a Mecanum Drive? If that's the case, this is a great robot to throw together if you don't have the budget to be able to put up Mecanum Drive, but still allow you to be able to get a Holonomic Drive setup. Another interesting setup here is called H Drive, where it's kind of like your 4-tank drive, but instead of using traction wheels, you're using omni wheels, and you have a 5th omni wheel in the center that allows you to strafe left and right. So let's take a look at this little H drive here, where it does have holonomic, and you have a single motor in the middle that allows you to move left and right. So you get a little bit of traction moving forward, probably a little bit better than on a Mecanum drive, and you have a 5th wheel that allows you to strafe left and right, so that helps it up. So it's kind of a good compromise between that X drive to be able to get a little better strafer power, but not quite up to the Mecanum. Again, you have a lot of these issues with being able to be pushed around. One big one here is that it's a little easier to get stuck because you have a wheel in the middle. It also makes it a little more complex to be able to design things around that. You've got a wheel in the literal middle of your robot, so it does make you think about how can I package things around. That being said, if you need the ability to nudge or strafe around like this kind of medical robot that's driving around, it can be a pretty stable platform, especially if you're just going to be boxing things up on top. So if you need some sort of strong forward pushing power, while also be able to make your precise sideways movements, an H drive is not a bad design to be considering. The last 2 designs are actually kind of both in the same. It's called Swerve Drive. And Swerve Drive has 2 kind of major setups. One here is this 4-pod setup, like we have in this design, where you have 4 pods with 2 motors each. One motor drives the wheel in a circle, and the other motor turns the motor around. So let's take a look at some video examples here. We've got a motor turning and moving this around as it follows an April tag. We've also got another Swerve Drive here being able to drive around, so we can see that one motor is capable of spinning the wheels to rotate, and another motor actually rotates the wheel along so that it can actually drive along that base. These are really commonly seen in competitive robotics with FRC. It allows you to drive your robot around, makes them very agile, which is a great design when it comes to Swerve Drive. So, and it really does combine the best of all worlds in that you have some freedom of movement of holonomic drive, but you get the grip and the pushing power of a tank drive. So Swerve drives are awesome setups for robotics. You have the ability to change direction anywhere you want. You've got great pushing power, just like in a tank drive, and you have all 4 wheels moving together. But they are also the most complex drive to be able to do, because each of these 4 pods has 2 motors, as well as a lot of different, depending on how you design it, gears, belts, chains, anything along those lines. They tend to also be a lot more expensive. Out of most of the other drives where you're only using 4 motors, you have to have at minimum 8 motors to be able to drive this, because you need 1 motor to actually drive the wheel and 1 motor to rotate the wheel. These are also really advanced to program as well. So despite having the best of all worlds, it also is the most complex, the heaviest, and the most power hungry of all designs. One thing to think about is, do you have the skills to actually design one of these? And do you have the skills not only to build it and to program it? As well, a great question, is the absolute GOAT, or the greatest of all time, in agility and power when it comes to robotic drivetrains, really justifiable for the task that you're trying to do? And that's a big question, especially in competitive robotics. Do you actually need a Swerve Drive setup? And is it really going to give you that advantage that you need? And does your team have the ability to actually program up one of these? Do you also have the resources to set these things up? Because these things are quite expensive and require a lot of custom machining, or a quite expensive pre-built part. Another option to Swerve is, instead of doing a 4-pod Swerve Drive, you can do a 2-pod Swerve Drive. It has the same kind of pod setup as a Swerve Drive does, but instead of having 4 pods in each corner, you have 2 pods in the middle of the robot, and the 4 corners of your robot are set up with omni wheels. So for instance, you can take a look at this robot here, where they have 4 omni wheels in each side, and we can see it actually driving around. It has a very similar kind of drive setup to Swerve, because it is a Swerve Drive. And again, we can see this robot driving around. It's got quite a bit of maneuverability, similar to another Swerve, but using a little bit less motors. And that's kind of one of the big benefits here. So a little bit less complex, and you have 4 omni wheels on each corner and 2 pods in the middle. So it still does set some agility and some movement, but it does get around some of those motor limits. So instead of needing 8 motors in total, you only need 4. Problem with this is that, again, it's a bit of a compromise in that now you only have 2 driving motors as opposed to 4 driving motors. So it's easier to push yourself around. It doesn't get that main benefit that Swerve Drive does provide. And it may start to get in sort of parallel with Mecanum. You may get slightly better maneuverability on a 2-pod Swerve Drive, but you can get less pushing power than you will off of a Mecanum. Some of this drive setup can be a little bit unintuitive, depending on how it is you're setting up, as well as your pushing power, depending on where it is you're pushing, you might not get the same as an actual Swerve. Again, you got a 2-pod Swerve here with one of these drives being set up on sort of a caster. This tends to be a bit more of a interesting design to think about, as opposed to something that, if you're going to be talking about this in competitive robotics, something that really ends up being competitive. And for the most part, it ends up being a bit of a proof of concept robot, being pretty cool, but it's not necessarily something that's the most competitive. And if you have motor limits, it's cool to see if you can do this. Now, if you have a more or less power-hungry design, you need something that's a little more compact than something in a full Mecanum drive would design if you're doing more of a DIY side of things. This is a really fun setup that you might be able to consider work through. If you're looking for some additional resources on designing drivetrains, you can consider joining up in the community down below, where I can give you some one-on-one feedback on your projects, as well as vote on future tutorials. There's other resources like Game Manual Zero and Produce Sigbots, has some excellent resources on designing some of these holonomic and tank drive designed points. So I hope you found that a helpful overview in the types of different drivetrains that exist, as well as some important questions for you to consider for what drivetrain might make sense for your project. If you got any questions, let me know in the comments below. Otherwise, best of luck on your next robotics project.